idea is to calculate, in fact, the weights here, as we can see here, and some other, which are the internal weights here, as the same. Okay? So, in fact, the difficulty was how to learn. In fact, to learn this one is the same than before, but the problem was how to learn automatically these other weights here. And for that, it was the researcher who worked on about that, okay? We were, in fact, Rumeralt and Hall, okay? Here, sorry. And also in Lequin, okay? So they introduce, in fact, gradient of error calculation, which means, in fact, it's a back propagation rule, okay? I will not discuss about that just during this lecture, because it's not necessary at this level, because it's an introduction of artificial intelligence, okay? But in fact, it's not really necessary, because now we have different tools, different programs which can implement this gradient of error or backpropagation rule, which is in fact very we can find very easily this kind of program, as we see that during this lecture. Okay, so the idea is using this backpropagation rule, we can calculate all the weights here and this one also. Okay, and this backpropagation rule is also used in a deep neural network. Okay, so thanks to this one, so we have also, as I explained before, we have also an activation functions, nonlinear function that we put on the here, because in fact we have to calculate, as I explained, in fact, the multiplication between this weights here with this input, plus this weight multiplied by this input, and so on, okay? And on the output, here we have the nonlinear function, and as I explained before, it should be, for example, the exponential function or a simple threshold function, and we send that directly to the output, to the input, excuse me, to the next layer here, okay? So the nonlinear output here is sent to this one, to this input here, and so on again, okay? Okay, so now let's see again for the XOR function. So here, what we have, in fact, so we find, okay, in fact, we have the perceptron, the output perceptron here, okay, that we want to obtain, and in fact, we introduce an internal layer here, which is, in fact, the name is hidden, which is a hidden layer, okay, internal layer. So here we have x1, which is, for example, A, x2, which is B, okay, and these two inputs are connected to two neurons, here, one neuron here, and a second neuron here, and each of them we have a connection through different ways. It's the same that we have seen before. And here, so we have the internal weights here to calculate to the same here, okay? Okay, so with this one, so we can solve directly the nonlinear function that we have seen just before. Okay, and it works correctly now with a second layer that we have introduced here. If we generalize this one, as we can see here, so we have in general, okay, for the multi-layer perceptron, and the name is MLP, okay. So we have the input here, which is connected, which is this one, in fact, which is connected to different neurons here. The name is hidden neurons or hidden nodes, okay? And here we have, we can generalize all that. We can have n layers, as you can see here. And that is the case, in fact, in a deep neural network, because we can find 2, 3, 4, 5 layers of neural networks. Okay. Okay. Just to finish this presentation concerning the second lecture, here, so we have some, as I explained before, so we can find different library, Python library. As I explained before, we have the scikit-learn here, so we can find that using scikit-learn.org, and we can find all the classification explanation here. I discussed already about that. And another one, in fact, for the inside this one, okay, so inside the scikit-learn library, so we have a specific case, which is a MLP classifier. So you can test by yourself directly the MLP classifier for different examples. Okay. So, and you have some tutorials about that, and you can read that for more explanations by yourself. Okay. So that was the end of this, just to remind you different basic information. So now you can go to the third and last lecture for this session. And I will speak in more details about now about deep learning. Okay. And as we will see during this lecture, this part, in fact, in deep learning, we'll see that all the topics that I discussed before, here and here. So we'll see that again, because we will see that, in fact, in deep learning, it's a generalization of, in fact, the perceptron theory. Okay, so let's see the basic operation in deep learning. And in fact, the basic operation in deep learning is convnet. Okay, and convnet means convolutional neural network. And convolutional is a word which comes from, in fact, from signal processing and image processing. Here, as applied to also deep learning for image classification, image recognition, and so on. Okay, so we can have a 2D convolution, as I will remind you just before. Okay, in fact, as you can see here, so Lequin, Bengio, and some others introduced a first convnet in 1988. Okay, and here we have the name of this one is of this convolutional neural network is LeNet. Okay, and it was first applied to document recognition. Okay, so for handwritten recognition, as I explained before. Okay, so as you can see here, so we have the input, and it's a very small image. It's a 32 by 32 image. Okay, and here, so we have a first layer, and here, this, as you can see here, we have 6 layers of convolution. So it's like convolution. I will explain what is a convolution just after. Okay. Here, after that, so we have, and I will explain what is the difference between this convolution and the convolution in image processing. But just to explain a general introduction to this convolutional neural network, I continue here. So here, so as we can see, we have we apply the 6 convolution in parallel for the same input image. So we have 6 layers here. On the output, so we, in fact, we divide by 2 the size of the image that we can obtain. So in fact, we do, as we explained, a subsampling. So we divide by 2, we take 1 pixel by 2, okay, and 1 line by 2. So it means that on the output, so we have 14 by 14, the size here, okay, in theory. So here, so we have 6 output and 6 small image on the output, and we send each image, okay, to a next convolutional map, okay, here, convolutional layer here. So here, as you can see here, so we have 16 convolutional layer here. Again, we have in fact, a subsampling, okay, so we divide by 2. And at the end, we have a 5 by 5 size image. It's a very small image. And we send that after that to MLP. Here it's a multi-layer perceptron. And at the end, we want to recognize, in fact, here we have 10 output because we want to recognize only 10 different characters here, okay? Okay, that is what we have as introduction. So now we have to examine in details each operation that we have here, because as you can see here, we have convolutional operation. So it's like convolutional, it's like filtering in image processing. So I will discuss about that in a few seconds. Here we have the subsampling operation. So I will discuss about that. So again, we have the same here. Here we have, as you can see, full connection means that we have a MLP here. So I will explain that and how to transform also these small images here directly in vectors. I will discuss also about that in a few seconds. Okay. So first, we have, excuse me, I have to come back in, okay. So I would just like to remind you what is a convolutional in image processing. In fact, the convolutional theorem is used, in fact, to discuss about image filtering. So if we consider on a specific box, this one, which is the filters, the 2D filters, here, so we have the 2D images, okay? F means that it's a gray level here, and X and Y are the coordinates of the image, of the original image, okay? So what we want is to do some filtering, for example, how to eliminate the noise inside the image, okay? So for example, here, just to discuss about that. So for example, here we have an original image, okay? And so it's written in French, so it's the same than it's very close to English. Okay, it's the original image, and here it's a filtered image. Okay, so the idea, for example, so we have the f of x and y. Okay, so it's a input image here. So as you can see here, we have a lot of noise inside this image. So the idea is to eliminate or to reduce the noise on this input image. So the output is this one, and this filter that we have here, so I will present that just after, is like smoothing, image smoothing. Okay, so let's come back to the to this operation. Excuse me. So here, so we have this 2D filter. So there is a mathematical explanation about or description about this filtering, and in fact we have here the H function. H function is in signal processing theory. The name is impulse function. Okay, so we in fact which is a function of the filtering. Okay, so we can just do a very simple explanation or to remind you what is convolutional, okay? So it means that here, so we have to apply to each pixel of the image for X and Y, okay? So we have, in fact, to apply this filter, and it means that in the neighbor pixel from the center X and Y, so we have to apply this one. So it means that in fact, what we do, we can consider neighbor of n rows and m columns around the central pixel that we want to examine. Okay, so we want to filter the red the pixels, which is here in red. Okay, and we have all its neighbors pixels here. Okay, so we have a size. For example, here we have only a 3 by 3 neighbors. Okay, but we can consider 5 by 5, 7 by 7. N can be equals, and M equals to 7, 9, 11, and so on. And here, so what we do, in fact, we multiply the center pixel here in the actual pixels or current pixel here, which is at the coordinate x and y, okay, x and y, and we do the multiplication between this value here by the corresponding coefficient here, which is the h in n and m, so h minus 1 and m minus 1 here, and so we multiply this coefficient here by the pixel, the value of the gray level in this position. After that, we do the addition here with the coefficients, which is here, and so on. Okay, and at the end, we replace, in fact, this value by the new value that we obtain here. Okay, so this one, just to remind you, is a convolutional operation. In general, when we want to represent that, because we don't use this equation at each time because it's very heavy, okay, to write that. So, in fact, we can compact this this writing in only one operator, which is this one, which is a star, okay, and it means that it's the 2D convolutional product, okay, and the equation is, the detail of the equation is here. Concerning this neighbors here, so the name of h, in fact, for the impulse to the function, so we can use a mask function, or in more general, often we can also find the word of kernel, okay? But in fact, the kernel are directly the coefficients, in fact, of the filter that we can use. Some examples that I already described just very quickly. So the idea is, for example, some examples. So this one, for example, I can show you, for example, an example of edge coefficient of kernels. So here we put 0 on the corners here, and we put 1 on the other for the others. And here is the 3 by 3 filters kernel. Okay. So what we mean, in fact, so we can multiply for each. So I can show you an example. Okay. Here. So again with this one, so I can have this kind of coefficient here. So as I explained before, if I consider here this one, the sum of the coefficient here is plus 5, because it's the addition of all the value which are here. And what we do, I can put an example. So the original image for me is this one. So we have 7, 7 anywhere, but we have only one pixel, which is at the value of 0. Okay. So it means that, for example, if we call this image 7, for example, should be, for example, the white, okay, the background of the image, white, and 0 should be, in fact, black, okay, so it means that we have a noise, just a simple pixel, which is, in fact, which corresponds to the noise. So what we want to do is to reduce, in fact, the difference between 7 and 0, and just to have a smoothing, in fact, of this, in fact, artifact of this noise. Yeah, okay. So what we do for each pixel of the image, so we calculate, in fact, we apply, in fact, this function, this convolution function. So let's see, for example, this one. So we have the neighbors, which is in the red box here. And so we have, in fact, we multiply, in fact, this value, or not this value, but we multiply the corner here 7 by 0, so it's 0, plus 7 multiplied by 1, plus 0 multiplied by 7, plus 1 multiplied by 7, plus 1 multiplied by 7, plus 1 multiplied by 7, plus 0 multiplied by 7, plus 1 multiplied by 7, plus 0 multiplied by 7. So it means as we have 4 values which are at 0, so it means that the value here at the end will be 0, okay? So, and if we do the addition, it means that we'll have the addition of after this multiplication, so after this, after this operation, okay, because we do the multiplication and the addition, okay? So it means that we have 35 here, okay? So because it's 7 by, we have only 5 pixels which are with a coefficient which are 1, okay? So it means that we have 35. And in the equation here, we divide by the summation, okay, of the coefficient here. Here we have the coefficient sum is 5, so we divide by 5. So at the end, the value here will be the same because it will be 7. So we can now continue. We can go to the next here and so on. So for the next here, so the average will be the value will be the same, okay? But the only difference will be, for example, here. So if we can consider this one, so this one, which is in the blue box here, so we can see that here, so we'll have this one, so it will be, in fact, we'll have 7 by 0 and so on, and here, the 1 by 0 here. So it means the multiplication and summation will arrive at 28, and 28 divided by 5 equals 5.6. And if we do if we use the nearest integer value, it will be 6. And at the end, so we'll obtain, in fact, this one, okay? And it means that, as you can see here, so the difference between the 7 and 0 has been reduced, okay? So if we consider that 7 is white, okay, so it means that 6 is not so far to the white, so we reduce, in fact, this noise, okay? That is what we have seen here. So as you can see here, so we have a lot of noise, and the output here, so it's not excellent, but we can better recognize, in fact, here the object inside, which is a woman face here. Okay. There is also just a discussion, because just a consideration when we do that, it's just a discussion about image processing. In fact, what we have seen here, so here we have only 1 pixel, okay, which is different to the others. And now we have propagation, in fact, of the difference here on the neighbors here, because now we have, in fact, a simple pixel. Now we have a few pixels which are different. Okay, so it's like when we do some photography and we do some defocalization. Okay, we defocus the lens of the camera. Okay. And in fact, as you can see here, so okay, we have a very black pixel here, which corresponds in fact to this one. But if we do the, in fact, this smoothing, which corresponds in fact to, we defocus, in fact, the lens of the camera. In fact, as we can see, we reduce the difference between the background here and the gray level here. Okay. But the pixel, we increase, in fact, the size, in fact, of the of the pixel. So it's like a blurring. So okay, we reduce, in fact, when we do smoothing, we reduce the noise, but we put some blur, inside the image, because here this image is just a little blurred. Okay, that is an example. And a second, okay, that was what I obtained. Okay, just to no, it was just excuse me. What happened? Okay. Okay. So okay, can come back here. So as we have seen here, so here, so we put this value, okay, and now the difference between, so we can find some others. So here we have some others. Here we have, for example, we put one here. Or also, we can put also contrast increasing, okay, like this one, okay, and we can put that, okay. So the difference now between the convolution in image processing and convolution in deep neural network is, in fact, in image processing, we know we fixed, in fact, the coefficient of the filtering, okay, and the difference between this image processing operation and in deep neural network is, in deep neural network, we don't know the coefficient here, but we learn this coefficient, like in perceptron. So it means that these coefficients of the filters coefficients of the filter kernel, in fact, corresponds, in fact, to the weights in perceptron operation. So it's the same. So the difference is, again, in image processing, we know we have this coefficient or this weights. These weights are like a constants, okay, in image processing. But in deep neural network, we learn for the specific application, we learn, in fact, this coefficient. Okay. So now here it was an explanation about the convolution. For example, here I have this example, okay, and on this example, so I have 6 filters in parallel, okay, and in fact, we learn the coefficient of these 6 filters, and these coefficients are directly, in fact, the weights of this neural network. Okay. Why we do? For which reason we use, in fact, convolutions in deep neural network? Let's see now. First example here. So here we have in fact, the standard dense layer for an image input. Okay, so it means, in fact, it's like in fact a simple perceptron here. So in fact, here we have 640 VGA images. Okay, VGA. We have 64. Excuse me, 640 rows, okay, and we have 480 columns, okay, and here it means that we have a color image because we have 3 channels, okay, and as we have seen in my previous demonstrations. And so we have a matrix. In fact, we have three matrices of gray level: red, green, and blue here. Okay. So we can consider. So here it's written in Python. Okay, and we explain that after. It's like a Keras library. And here, so we have we consider that the X is the input. Okay, so it's written in Python, and we consider, in fact, we put that also in floating point, okay, on 32 bits here. Okay, and the idea for which reason we do that, because in fact, when we do after some numerical operation like convolution and so on, So we need to work in a floating point representation. Okay, here we have using in fact this specific package, which is we see that after that in deep neural network. Okay, it's Keras. Okay, so we transform in fact this one in big vector. Okay, so it means that maybe we see that here. Okay, so we have this image here, so this color image here. So as I explained, okay, and we take the first pixel here, which is the first element of this vertical vector here. And after that, we take the first pixel here, and we put that here. The third element here would correspond to the first pixel here. And after that, we take the second pixels here, we put that here, and so on. And at the end, so we have all these pixels. So we transform, in fact, this 3D, this image, this color image, in fact, in a vertical vector here, as you can see. Okay, and the operation in using this specific package, the name is flatten. So it's a specific operation in Python, and with a specific package which is Keras. So we transform that this 2D representation in these three matrices, in fact, in a 1D vector, as you can see. If we calculate the size of the vector, as you can see, so we have the size of the image here, 640 by 480 multiplied by 3 channels. So it means that this input vector is close to 1 mega elements, 920 elements, as you can see here. So we have a big vector here on the input. Okay, so when we do that, so it means that we have here this one, and after that, so we have this one, okay, and after that, so it means that we can put here, so with dense means that it's the name again with this specific package. The name is Keras again. I will speak about that in a few minutes. So in fact, for this example, we consider a perceptron with 1K neurons. Okay, so it means that we connect each element to this 1K neurons here. Okay, so as we have something like 1 mega elements here, so it means that we have 1 mega here multiplied by 1K here. So it means that we have a very huge weights, number of weights here, because we have all the connection here. So I just represented some of them, okay? But we can imagine that we have to connect all this one to this one, and so on, okay? Okay, so just this representation, this simple representation, as you can see here. So we can, in fact, with some instructions, as you can see here, we have only 1, 2, and 3, because these one are comments, okay? So as you can see, we can represent this simple neural network with only three instructions of programs, of Python programs here. Okay, so here, that is the first programs that we can find in this one. The problem is, as I explained, okay, so is, as I explained here, so we have something which is very huge, because we have something which is close to 1 giga, in fact, weights to learn. So it's very huge, because 1 giga synapses is very huge and it's very difficult, in fact, to implement. And it takes a long time to do that, even with GPUs, okay? So we need to reduce the size of parameters or weights that we want to learn. So it means that it's close to the coefficient. So we can imagine that we have something close to 1 giga weights to learn. So it's very huge. Okay. The idea is, in fact, the reason, in fact, to introduce the convolution was, in fact, the reason mainly is to reduce the size of this parameter here. Okay. Okay, that was this one. So, for example, here, so as you can see, I have another example of operators that we have here. Here, we don't use, in fact, so we have here fully connected neural networks with multi-layer perceptron. So again, here is the same that I have explained before. So here we don't have, excuse me, here, so we have this one, so we have a dense here, okay? And because, as you can see here, so I will explain that in more details after that, okay? Just now to come back here, so we can have this one. So this one, it's again with convolutional neural network. So we don't use, in fact, the flatten, okay? Because again, if I calculate the number of connections, it will be here very huge. Here, as you can see here, so I use a very simple, very small image here, which is a 28 by 28. Okay, is the example for the handwritten character recognition. Okay, just to remind you, it was this. Excuse me, it was this example. Okay, so the 32 by 32. So here, if I consider this one, so I have this image, and here I consider, in fact, on this input, after that we apply 32 filters, and conv2D, in fact, is a convolution. Okay, so again, for that we can use a convolution through using, in fact, the Keras package, as I explained after. So here we have, in this example, so we have a convolution, so we have 32 filters in parallel. Here we have 5, it means that here, so we have a kernel, the size of the kernel is 5 by 5. In my image processing example, I use a 3 by 3 kernel. Okay, so here it means that I define 5 by 5 size of the kernel, and on the output of this convolutional, I have a nonlinear function, which is a ReLU. I will speak about that in a few minutes. Okay. After that, I have here, so the convolutional here, so I will speak again about that just after. Here we have here a nonlinear, so it's a nonlinear. So here I have the subsampling function. I will explain that after that. And after that, so we have, in fact, when we do that, we have 32 output. And each output is sent to each of the 64 input here, and again we have 64 layers here, and so on. And at the end, we can use, in fact, only we transform the 2D representation in a 1D representation using the flatten instruction that, as I explained before, but the size of the vector will be very small in comparison with the previous one that I explained. Okay. And at the end, we have some layers here, as I explained before. I will come back to this slide after that because I need to give you more explanation. So just to remind you how to consider this convolutional operation. So I explained, in fact, the convolutional operation in details with my image processing example before, okay, with the smoothing example. So as I explained, the difference with deep neural network is that we have to learn and not to put constant for convolutional. Okay. We add after that, after the convolutional operation, excuse me, we add in fact the nonlinear function here. Here, that is, for example, there is, for example, the ReLU function. And so we can find, I will come back to this one. So we have some nonlinear function, and the name is activation function as this one. In fact, what we consider here is if the input of this nonlinear function is negative, we put 0, that is a ReLU, okay? And if the output is positive, okay, the output will be the same than the input. So it means that if we consider not this one, okay, so the name is this one, okay? So as we can see here, so if we are in the negative part, so it will be 0. And if we are in the positive part, so it means that if we have 10 here, we'll have 10 here. So the output will be the same than the input. So see, that is the first. The second one, I introduced already that in my previous lecture, okay, using in fact my example of perceptron applied to the simple logical function. Here I use a sigmoid nonlinear function. The equation of this one is like that. So it means that if we are in the negative part, okay, here if we have minus 10, it will be 0, okay? And if we have here 10, on the output, it will be this one. But when we are close to 0, so the exponential is used here, as you can see here. So it's a nonlinear output. So these two ones are very famous in neural network. Okay, that is what we put at the output of the convolutional or about the perceptron, for example. Okay. And there are some others. For example, we have the softmax function, and we have also the softplus function, which are this one. Okay. Generally, we use the ReLU just on the output of the convolutional layer, okay, and or the sigmoid, but in general we use now ReLU function, okay, and at the last output of the deep neural network, we use either the softmax or the softplus or the softplus function, okay. And the equation for the softmax is this one, okay, okay, and is this one, and so on. Okay. So that is what we put on the output of the convolutional function. Just to come back here to the convolutional function. So as I explained before, so we have a kernel, okay, 3 by 3, 5 by 5, and so on. Just at the output, on the output of the convolutional layer, so we put this nonlinear function, for example, the ReLU function, as I explained just before, and we apply that on the input. Here, for example, so we have, in fact, so we have here, so we have the color image. So the size is 28 rows by 28 columns, and we have 3 channels. Okay. In mathematical representation, in fact, when we have this one, is as you can see, we have 3 matrices. Okay, and the mathematical name for that is a tensor. Okay, so a tensor, in fact, is a concatenation of different matrices of the same size. Okay, so here a color image is a tensor of with 3 channels. Okay, so the name is a tensor, and we, for example, here, we can apply, in fact, this one to 5 by 5 size here. Just to come back to something, because there is, so we can have here, so we have only one convolution here, so apply to each one here. And so it means that we have 5 by 5 is the size of the kernel. And for each color, we can apply a specific filter or specific kernel. So we have 3 different kernels here for the color image. And the size of the kernel in this example is 5 by 5. But we can also have multiple convolutions. Okay, for example, so we can have we can multiply by 4 this one, so we can have 4 operations like that here in this example. Okay, so here, so we have 5 by 5 kernel size, 3 different channels, so 3 different filters, and we can multiply by 4. So it means that we have, in fact, 3 by 4, it means that we have 12 different filters multiplied by kernels of 5 by 5. Okay, so it means that we need to learn, in fact, the number of coefficients of the full filters here will be 25 multiplied by 12. So it means that we have something close to 300 coefficients to learn. 300 coefficients, or if we use a neural network language, 300 something close to 300 synaptic weights to learn. Okay, that is the difference again with original image processing. So in general, we use 3, 5, 7, 11, okay, size of kernels, and sometimes it depends of the operation. We can use also only 1, okay, but generally it's between 3, 5, and 11 size of kernels that we use. As you can see here, the size of the output will be, in fact, because we can have 4 here, okay? And we can see that here is not 28 by 28, but here, for example, is 24 by 24 here. Here is something that I don't discuss before. I will come back to the image processing convolution example, because in fact, it's a border effect. What is this border effect? Here, as you can see here, in my example, I began my operation, my calculation here with a second row here, second line, and second column here. Because why I use that? Because if I began here, for me it will be impossible to calculate, in fact, these pixels in regards to the previous one, because the previous one does not exist. Okay, so in general, in image processing, if we have 3 by 3 kernels, we begin with second and rows and second columns here, and we finish also just before here, and the same for the last rows here. Okay, so in this example, we reduce the size of the final image, of the output image, because we don't calculate this one, the border here. That is what I mean by the border effect. Okay, and we have some solutions. In fact, if you want to keep the same size, should be in fact to add virtual pixels here. So, for example, we can copy this first line and to put that here. Okay, and the output size will be the same. Okay, but sometimes it's we don't do that. So in fact, we prefer to reduce the size of the output, and in fact just to have on the output this one and this one. So it means that the size of the output will be reduced, and the size of reducing depends in fact of the size of the kernel here, and that's the reason why here. Okay, so we can see that as we have 5 by 5, so it means that we don't calculate in fact, the first line and first column here. So we have just the border. We don't calculate, and we have on the output only 24 by 24 pixels. Okay. So we discussed about the nonlinear function before. Okay. Now I would like to speak also about the stride. Okay. So it means that it depends, in fact, of the strides corresponds, in fact, to the step of what we want to calculate. Okay. So the stride, in fact, excuse me, here, so we can consider this one. So it's used for the subsampling. Okay. And here, for example, we can have the to this one, to this pixel. So we have a 1, 2, 3, 4, 5. Okay. So I can calculate this one. So if I use this one, so I have a kernel. Okay. But if I do a stride of 2, it means that I don't calculate each pixel by each pixel, but I calculate that with a step of 2 here. When I put a stride of 2, it means that I calculate with this one, and the next window which will be considered will be with a step of 1 here of 2. So this position, and we consider this next position here. Okay, and we can calculate these pixels for this one. Okay. Again, here it's related to what I explained just before about the bordering effect. Okay. So there is a technical word about that. We can, as I explained, we can fill the border. Okay. And if we want to keep the same size, so we use a padding operation or padding instruction. So sometimes we use that, or sometimes we don't use that. Okay. So if we use, for example, with this one, if we use a padding operation, so we'll have on the output the same size. And if we don't use this padding, so we'll have reducing the reduced size of the image here. Okay, so that is what I explained about the strides, about the padding. Okay, and now the next operation which is very useful is pooling. So the pooling, in fact, is used, and generally we can also combine that with a stride. No, stride, it's related to the in fact to the step. Okay. In fact, it's after the convolutional with and after the nonlinear functions. So we want, in fact, to have the subsampling operation. Okay. So as I explained here, no, it was just at the beginning. Okay. So I would like to speak about now the subsampling. Okay. So what we have. Here, okay, here, so to do the subsampling, we use what we name, in fact, is a pooling operation. So, and the objective of this pooling operation is subsampling, in fact, is to reduce the spatial dimension. Okay. So, for example, here, so what we do the average. It means it should be linear or non-linear. Here, what we do, in fact, we calculate, in fact, the maximum, for example, in a neighbor of 2 by 2. Okay. So it means that here, so we consider this window, which is 2 by 2 pixels. Okay. And we take, in fact, the maximum in this area. It's like if you are familiar with image processing, it's like what we use in morphology mathematical operation, okay? And it corresponds, in fact, to the dilation operators. So we use, in fact, the maximum in the local area here. So the maximum here is 6. So we reduce the size, which is 2 by 2 by only one value. and we take the maximum. So the 6th year will be 6 year. It will be the same for in the next window here, and the maximum is 8, and so on. Okay, so here it will be the 3, and here it will be 4 here. So at the end, so we, as you can see, we have the subsampling by 2, okay, and the stride by 2 because we don't have, in fact, we don't have this window, for example. We don't consider this window because we have a stride by 2. We have, okay, we have a step by 2. So we take this one, this pixel, and after we have a second pixel here. Okay, so I explain the convolutional operation. I explain the nonlinear operation using, for example, the ReLU function. I explain also the pooling function, as I explained here, and also the padding function, in fact, to keep or not to keep the same size of the image. Okay, so that is some basic operations which are used in deep neural network operations. Okay. Another one I will come back after about that is when we do the learning. For example, here I have a multi-layer perceptron representation here. So as you can see, each neurons are all connected together. Okay, so I have all the weights here. When we do that, we can have some overlearning. Okay, so I explained that during my previous lectures. It's a problem because if we want to have some generalization, it does not work. So the idea when we do the learning is to do some drop out. Okay, so what we do, we don't learn and at the same time all the weights, all the connection here, but we learn some of them. So we eliminate all this one. And so that is what I explained by drop out. So for example, we can here, so we can keep only 10% of the weights here. So we learn the first 10%. And during the next step of learning, we'll use some other connection again. And in fact, we do that with a random deactivation, okay? And we do that for each training epoch, okay? So when we do that, we avoid, in fact, the overlearning, okay? And we do that only when we do the training, okay? When we do the learning, okay. Just to speak now about something, in fact, as I explained, I spoke about Keras library. In fact, as you can see here, so different companies, but also universities propose from the 10 last years different frameworks how to, in fact, to design specific neural network. In fact, these frameworks are always, in general, used for in Python, and it corresponds, in fact, to specific packages in Python. Okay, so they propose different packages, and in fact, it was introduced by the big companies in like the GAFAM, so Google, Apple, Facebook, Amazon, and Microsoft. Okay, and some others were proposed, for example, in France with the CEA, which propose a specific framework here and 2D2. But in fact, the most famous are from Google, and they propose, in fact, two specific packages that we can use in Python. Is TensorFlow. Okay, so TensorFlow refers, in fact, to tensor representation, like the matrix with color images, okay, as I explained before. So the name of this package is TensorFlow, okay, and which is very efficient but difficult to use because it's very specific instructions, okay. And there is a an easier package, which is Keras, as I mentioned before, and I will come back to this specific package after, okay? And all this, in general, all these packages are free to use, okay? So they are open source, okay? So we can find with Google, in fact, TensorFlow and Keras, and myself, I use this one, but some of them are maybe some more efficient, like in Facebook, PyTorch is one of them, and also Café. And PyTorch is maybe very interesting. So in some cases, we can use also this one, okay? And Microsoft also propose some others, Amazon also. I know that Intel propose also some others, okay? So we can find maybe 10 or 20 very popular frameworks from different companies and from different universities. For me, for this introduction, and to begin with deep neural network, I suggest to use Keras, as I explain after, okay? Just to come back to, excuse me. Okay. As I explained, I suggest to use Keras. Okay. So, and it's very interesting because you can install that directly, and it works on different platforms. Okay. And with or without GPUs. Okay. So it's very easy to use. And to install Keras, so I put here some subjects, some instruction, or some examples how to install Keras. So again, so we can use pip install, as I explained before. And so it's we need, when we want to use Keras, we need also to install TensorFlow. So we need to install these two packages, okay? So with that, we use pip install TensorFlow and pip install Keras. And after that, we can use directly this one. Another one, I will explain that also after, is Jupyter. So Jupyter is also a specific platform also, which is very useful. And I will give some demonstration after. Because we can use that directly through, in fact, the web representation. It's very easy to use. I will show you some examples. So, and after that, that is just to install some others. So, for example, some other packages. For example, this one is, in fact, how to store and to load also in fact, all the weights or all the coefficients that you have learned. During my second lecture, I have shown how to save the weights, the coefficients, for the simple Python example, okay? And I use a CSV file representation. It was, for me, simple representation. But in general, when we have more than 10 or some hundred and thousands coefficients, it's better to use some specific files, okay? And one of them is H5 pi representation of files, and which is in fact a standard, okay? How to store, in fact, all the coefficients and how to load them, to use them after. Okay, so we have some other library, so like Pillow. So we see that. So for example, with Pillow, we can use effectively CSV files and so on. Jupyter, I explained that. So it's very useful. In fact, description or platform how to use, in fact, deep neural network. And we use that. Label image is a very interesting package because it's used for how to do the annotations of the image. Okay, and okay, so I spoke about, for example, matplotlib. So it's we use that already, and NumPy, and also OpenCV. So you know that also. Okay, but as a minimum is in fact how to to install, in fact, TensorFlow and also Keras. So you need to use this one. Okay, so I would just like to come back now, as I explained all this instruction. I would like just to come back to, in fact, to my examples that I explained before. Okay, so here now, as I explained that, so here that is for the multi-layer perceptron. Here, so here I have it's not convolutional. Okay, it's just the multi-layer perceptron. So it means that now we have again only there is only one channel. So it means it's a black and white image. Okay. So we have a size of 28 by 28. Okay. So here I have the flattened. So it means I transform this 28 by 20, in fact, this 2D image in a 1D vector representation. Okay. So the 28 by 28 is something like close to 800 elements. Okay. And here I have a first neural network here. So we have 256 neurons on the input. And here I have an activation. So as I explained, it's a nonlinear output. So it means that the output of the previous, of the calculation of the coefficient, if it's negative, the output will be 0. And if it's positive, the output of this nonlinear function will be the same than the input, okay? All these 256 output of neurons are sent to a second layer of perceptrons. Here I have 10 layer of perceptron as this one, and on the output, so I have directly the layers here. Here for this one, so it's now with a convolutional neural network. So again, I use the same image here, this one. And now what I have here, so I have a first layer, but we have 32 filter in parallel. The size of the kernel is 5 by 5. I have the nonlinear function, which is a ReLU here. After that, I reduce the size by 5 by 2, okay? Because I have a max pooling of 2, so it's a 2 by 2, okay? So I have a subsampling by 2, and I have a stride of 2. It means that I have a step of 2 pixels for each calculation, okay? So here, the 32 output of this one, so it means that on the output, I will have a size of 14 by 14, but it will be not 14 by 14, it will be minimized because we have the border effect, but okay. After that, I have again 64 filters in parallel applied to each 32 outputs here, and the kernel size is 3 by 3. And the output, again, is applied to a nonlinear function, which is a ReLU function. Again, we have a subsampling here, and with a stride of 2, so a step of 2. And after that, after all that, I have the flatten here. So it means that the size here, we see that in more details after, so will be reduced. Okay, so the size of the vector will be maybe something like, if we see that just after, because it's difficult to explain that only with this slide. And at the end, I have here a multi-layer perceptron. It's the same than this one, okay, which is applied here. And after that, I have the my neural network, which is learned here. Okay, so now let's come back to, let's go, excuse me, to the example. So I would like to give you a first example of a deep neural network, which is very famous, which was introduced maybe 7 or 8 years ago. Okay, so in the history of the deep neural network, in fact, it's a very old deep neural network. So it was introduced in 2012 or 2014, I don't remember exactly, but okay. So in fact, this AlexNet is the name Alex. It was the first name of the guy, of the researcher who introduced this, in fact, this deep neural network. Okay, so he used, in fact, different filters. For example, 11 by 11 on the first layer. Okay, so it was, and he used, in fact, 96 filters in parallel on the first layer. So it's very huge. Okay, and he used a stride by 4. Okay, stride 4 here. Okay, so that is what I have here, and so on. Okay, let's see in more details what we have. So in fact, we consider here this one an input image, and the size of the input image is I think there is a mistake here. Maybe it's 227, but normally it's 224. But okay, it's very close. So here that is the input image. The size is 227 by 200 by 27 pixels, and we have 3 channels. So it means it's a color image. Okay. Here, so I have, I consider here this one, and here it means that apply this. Okay, I understand now. Here I have 96 filters. Okay, and with 11 by 11 kernels. Okay, but with a stride by 4. So it means that we divide by 4 the number of this one. So if we multiply that by 4, it's close to 200 by 27. Okay, so there's a reason at the output of this one. So we have a 55 by 55. Okay, and okay, and after that, so we apply. So with the max pooling, okay, we have here. So we have we divide by 2. And so that is the size of this one. Okay, so we have, in fact, as you can see, very huge number of filters here and here, and at the end we have here the multi-layer perceptron, which is this one, and here, for example, on this first layer we have 4K neurons. On the second layer of perceptrons, we have again 4K neurons, and at the end, so we have 1K neurons. So we have multi-layer perceptron with 3 layers here. Okay. A second one, which is easier certainly to understand, is VGG16. So VGG16 was introduced in the middle of the 2010, so it was 2015 or something like that. Okay, and there were some others after. So again, so we have here, as I explained, the real size, the exact size of this standard images is 224 pixels by 200 by 24 rows. Okay, with 3 channel because it's a color image here. As you can see here, so we have 6 in the first layer, so we apply 64 filters here, so we have 64 filters. Here, so as you can see, we reduce the size of the image by 2, so we have the subsampling, okay? So here we have 112 by 112, and we use, for each output, we use 128 filters. Again, we divide by 2. So here we have 56 by 56, okay? And again, we use 256 filters. Again, we divide by 2. So it means that we have 28 by 28. And now we have 512 filters. Again, we divide by 2. So we have at the end 14 by 14 size of the image, okay? And multiply by, okay, 512, okay? And again, we apply 7 by 7 kernel here at the end, and at the end we have, in fact, that is a size, in fact, of the vectors that I have to classify here using, in fact, as you can see here, so the directly the perceptron layer as the output. Okay, if we look to the programs that we can have here, so here, that is what we have here. So as you can see here, so the first thing that we do, that is as I explained before, so we use the Keras package here. And here, that is an example of using this Keras package, the Python instruction. So first thing that we have to describe, in fact, that is, excuse me, here, that is, in fact, this 64 filters here. So that is what we have here. So we mean that we have 64 filters applied to the input image here, which is, as I explained, the size of the input image here. We have 64 filters. Each filter has a kernel of 3 by 3. Okay. And the output of the filtering, we use, as I explained, the ReLU function. Okay. That is what we have here. Okay. Again, here, so we have a second filtering, which is here. So we have a second layer of filtering here. And again, we have 64 by 64 filter with a kernel of 3 by 3 and apply to the output here. And at the end of this first group here, so we have a max pooling because, in fact, we want to reduce, in fact, the size of the image here by 2 by 2. So we have a subsampling of 2. Okay, that's the reason why we have here 112 here. Okay, so as I have this one, so it means that now I have 128, in fact, images, okay, on the output here. So this 128 images, I apply again a 3 by 3. I do that 2 times, okay? So it means that I have 256 small images because I divide the size here, okay? And so on. And at the end, I have, in fact, the second, third, and fourth group here, which is the first one, second one, and fourth one here. And at the end, as you can see, I do the flatten, and the flatten is applied just here, okay? So, the flatten means that I put this 7 by 7 multiplied by 512. So I put that in a vertical vector here, okay? And here, as you can see, so I have a first layer of perceptrons here with 4K neurons, again with ReLU here. During the learning, as I explained before, I use a dropout instruction. Dropout means that here, for each epoch of learning, I use, in fact, 50% of the connections, and I random, and for the next epoch, I choice with a random choice, new connection and so on. And okay, and okay, so you have a first layer of perceptron here with 4K neurons, a second layer here, and at the end, I have this one with 1K neurons here, and it means that I have 1K categories which are possible to use with this one. Okay, so with VGG, I can classify 4K different objects, okay? And at the end, as I explained before, I have another nonlinear function, which is used here, which is a softmax function. Okay. Now let's see some examples. So just to finish, and we'll do some demonstration at the end before the discussion with you and some questions maybe. Concerning the application. So first one, as I explained, is the MNIST databases. I did an introduction in my previous lecture last week, during the last weeks. I remind you that this MNIST was in fact dedicated to the handwritten digits, okay, between 0 and 9. And in fact, I have different, examples. So we have for learning, we have 60K examples, and for tests, we have 10K digits, okay? Okay, so I will come back in my Python demonstration at the end of my discussion of my lecture in a few minutes. Okay, so first of them is this one. So is using, in fact, this one. So it was for the MLP here, and using Google Colab. I will speak about that just after. Or maybe no, no. Maybe I will discuss just about that after. Okay. So what I have here? So I will consider this. In fact, image. So I remind you that each image here is the size 28 by 28. Okay. Here I use directly the flatten. So as you can see here, so we have a transform here this image in a vector. So it was close to 800, as I explained before. So if we multiply 28 by 28, it means that it's exactly 784 elements. Okay. Okay. So I have this one. Here I have a first layer of neurons. So as we can see here, so we have we apply this 784 inputs to 128 neurons. So it's fully connected. So it's a first perceptron here. And the output of this 128 neurons are sent to a second layer of perceptrons. And again, the size is 128 neurons. Okay. So the output here, so as we can see, we have 128 neurons on the second layer. And here, so we have a third layer. And the output, we have, we connect all the connections of this second layer to the third layer. So it's fully connected again. And we have, in fact, 10 outputs because we want to recognize 10 different digits. Okay. So that is what we are using on this one. Okay, so I will come back to this example. I will do a demonstration using Google Colab just after that. Second possibility, in fact, to process this one is not to use directly MLP because, as I explained, we have a huge size of neurons and so on and connections. So a second possibility is to use the LeNet deep neural network, which was introduced again, I remind you, by Lequin in 1998. Okay, so now is to consider this one. So now maybe I hope that you begin to understand. Okay, that I have explained during this last lecture. Here, as we can see, we have 1, 2, 3, 4, 5, 6 layers of here. So we have 6 filters here. Here we have the pooling, so it means that we subsampling, in fact, this one. So it means that we divide by 2 the size here. Again, here we have 1, 2, 3, 4, 5, 6, 7, 8, maybe 16. We have 16 filters again apply to each output here. And here, so we have here the full connection here. So we do the flat, and after that, the full connection. If we find this one, so it means that we have that with Google Colab. So I will give you the example just after, as explained. And here, that is what I have here for this example. Okay, so here, that is another example. No, I don't. It's not a good example that I have here because it's not the same. I will explain that just after that. Okay. Here, in this representation, so as we can see here, in fact, we don't use for this example the same. It's another one. So here we have 32 filters, not 6. Okay, because here it was a simple representation with only 6 and so on. But in fact, in the place of 6 filters on the input, we have 32 filters. The kernel size is 3 by 3. We have an activation nonlinear function, which is ReLU again, applied to the input image. Okay, so on the output, we have a second layer here, so which is 64 by 64, excuse me, filters. Again, 3 by 3, applied to each of the 32 outputs here. Here, so we have again a max pooling here, 2 by 2. So we divide by 2. So we have the dropout. So it means that we use only a quarter of the connection for each epoch to learn. And again, we change that to next epoch. And after that, so we have flattened. So it means that the output is transformed, the 2D outputs are transformed in a vector. And here, so we have here the a first layer of perceptron. So here we have 128 neurons which are applied to the to this one. Okay, and on the output, so here, so we have only normally the number of class. And number of class is 10 because number of class was written here because we have here so 10 classes to learn. Okay. Okay, so as you can see in the Python program, so in fact we implement, so we use in fact the Keras Keras package. So we import the Keras package inside this example of a program, Python program. Okay, so we have the in fact directly the Keras package which is here, and we have some function inside this Keras package which are used here. Okay, we can find, for example, mnist. The database is new in the Keras. Okay, here we have dense. I spoke about that. Dropout and flatten, and we have also conv2d and max pooling 2d, which is used here. Okay. Here I define the size of the image, the input image. I can here, so I can learn. I can excuse me, load the databases mnist here, which is which come from this one. Okay, and I put that for the training. So 60K for the training and 10K for the test, as I explained before. Okay, that is what we have here. And okay, so here I prepare the image here, so that is just to do the twin. So we reshape, so we are sure that the size here will be 28 by 28. Okay, and after that, so we do a normalization because in general, as we know in image processing, the gray level are between 0 and 255. Okay, 255 means that we have the white level and zero level. But what we want to do in neural network is to have a normalization. So we divide by 200 by the maximum to have the value of the gray level, which will be comprised between in fact, between 0 and 1. Okay. Okay. So and after that, we can learn all this one. So if we do that, okay. So we do that, and through the Python program. And when we do that, as you can see here, so here I have 12 epochs, and the number of epochs are defined here. So we use, in fact, 12 epochs, and each epoch, so we use, in fact, 128 images and so on, and we can continue like that. Okay, so as you can see here, so we have at the beginning, so we have the loss, and the loss means it's the error, in fact. And as you can see, like for my simple example with the perceptron Python program applied to the AND logical function, at the beginning the error is high, but when I continue, so as you can see here, this error decreases, okay, and at the end we'll have a minimum error like that, okay. And when we have done that, okay, so we can have the result. Just at this level, I would like to give you an example here. Not this one. Excuse me, it's here. Okay. Okay, just before my lecture, okay, I I did this example, so I have to reconnect because okay, so I am using here. In fact, the Google Colab. So Google Colab is very useful because when it can be free, okay, if the neural network is not so big, okay. So for demonstrations or for simple examples, you can use that very for free access, okay. So that is what I do today, okay. And in fact, here, I use the examples that I have explained here. So if you come back here, so you have the link here. So I use this one, okay, this link that I have in my presentation here. So I use this one. And so for that, you have a Google account. Generally, anybody has a Google account, okay, and with a free access, okay. And I use this, okay, this access as I have shown here, and here is for the MLP, okay. So let's examine this one. So with Google Colab, so you can execute on some GPUs from directly at from Google. Okay, so you can access to the to the Google GPUs. Okay, and use that with a distance access. Okay, so here with with this one, Google Colab use, in fact, the Jupyter console. I spoke about that before. Okay, so with you don't have to install anything. So we use that with distance access. So Jupyter console is already installed by Google. You don't have to do anything. Okay, but if you want that to do in a local access using your own laptop, so you need to install Jupyter. Okay, so Jupyter is very interesting because we can, in fact, do a lot of comments, okay, inside the program, as you can see here, okay. So you can have some comments, some descriptions, so some tutorial if you want, okay. Okay, so as you can see here, that is some description from Google. It's a tutorial, okay, here. And here, so we have the program which is here. So first thing to do, as I explained, is to introduce, in fact, a different library like this one. Okay, you have seen all this one. Okay. After that, okay, so I have some also instruction like TensorBoard. TensorBoard is very useful. In fact, is when we do the execution of the program, it gives you some information about the GPU's occupation and so on. Okay, so first thing is first thing of my program. So I have, in fact, I can have defined, in fact, the data set. Okay, and as I explained, I am using the MNIST data set. Okay. Okay, so I define the size of the training data set. As I explained, it's 60K elements, okay, or examples, images, okay. Here, that is just to show you, so it's this one, so we can have some description. And for example, we can show, for example, one image from the 60K training databases. Okay, so if, for example, if we want to access to this one, to one of them, so here we have this image or this character which is shown here. Okay, so and we can show also here in this example we can show 25 images, small images here that is defined here. So we can check that by yourself. You see that. Okay. Okay. So now, as I explained, I normalize the data, as I explained before. And here, okay, so again, it's the same. And okay, now I build the model. Okay, so here, as I explained, here, so I have this one. So here I have 128 filters for the first layer. The second layer is this one, and so on. Okay. So here, as I explained here, so I have here. So as we can see, so I have it's the same as this one. Excuse me. I have to come back to this one. Okay. So it was with this one. So it's exactly this one. Okay. As you can see here, I have flattened. After I have 128 neurons for the first layer. Second layer 128, and last layer is 10, like this one. Okay, so if I come back here, so I have this one. So it means that I have the this one. Okay, so I have the flatten. I transform the 2D images in a 1D vector, and after that I have the first layer of neurons, first perceptron. The second perceptron here and the third perceptron here, as I explained before. Okay, and that's it. Okay, and after I run my program. Okay, when I want to do that. Okay, and here, as you can see, okay, so I have directly the description when I do that. Okay, and at the end I have this one. Okay, so that is what happens. So I can describe directly this one, and when I execute the program, that is what I obtain. So I did that before, and before my lecture, just was 2 hours ago. Okay, and as you can see at the beginning, here in this example, the error, the loss, which is the error, was 0.5, and at the end it was this one. Okay, but what is important, in fact, is performances. In fact, is the test at the end, and I see that with this example, in fact, the accuracy is more than 97% of accuracy. So I am sure that I can have this result here. So that is what I obtain, and here this curve represents, in fact, what I have here. Okay, that is the loss, which is represented with a graphical representation like this one. And here, that is, in fact, the accuracy that I obtain here. Okay, so what is very important is the test set here. So as you can see, it's here the orange curve, which is represented here, as you can see. Okay, okay. So, and at the end, so we have some tests which are applied to this one. So that is what I obtain. So for example, if I send 7 to test my program, so at the end, I have the output that I have here. So I suggest for you to test that by yourself. Okay, so it will be very easy to do. At the end, about that, that is, I spoke in my previous lecture about the confusion matrix. Okay, that is what I obtain here. So as you can see here, so with this simple example, so here, so I see that I have some, for example, that is what I want to obtain, okay, and that is what I obtain. So as you can see, so for the 0 digit, here we have 966 times I obtain the good results, and I had also some false detection sometimes. For example, there is a confusion between 0 and 2 sometimes. It's only 6 times, and so on. So we have the same here. And in fact, the ideal confusion matrix is if, for example, the classifiers, the neural network should be perfect. We do have, in fact, only the diagonal and nothing here and here, but it's impossible in the real life. Okay, so when we see that, we can see that the classifier is very good when we see that. Okay, that is what is explained here with the confusion matrix. We can see that in more details here, so we can see that sometimes there were some mistakes here. Okay, and that is just what we wanted to show. Okay, and as I explained here, it was the tensor board. Tensor board is to, in fact, to give you some log about how is used GPUs and so on. Okay, so just to finish, when we, so you have just to copy this website address. Okay, this one, which is written in my slides, and we put that here. So and when you do that, okay, so you have that, and if you want to execute, so it's in French, but execution means execute, and I can execute all that, and it works directly. Okay, okay. Just to finish my lecture here, we can have the same. Okay, it was. I come back here, so that is what I obtain here. Okay, that is what I'm shown here. So we can have also another application, which is a closing recognition. Okay, so in fact, there is a very simple example here. So again, I give you here this address, HTTP address, so you can copy that and to execute that, and you will see that it's possible, in fact, to recognize different clauses here, and for that, you use a specific databases. The name is MNIST Fashion, and you can use that directly and to test that. For that here, so we have another example of convolutional neural network. When I have a look about that, so as you can see, we have 64 filters. So again, the input here, the input size of the image is 28 by 28. It's black and white, okay? And so from this input image, we apply 64 filters. So we have max pooling and so on. We have a second layer of filtering here again, and max pooling again. And after that, we can put, so again, we have nonlinear with ReLU and so on. At the end, we have here the flatten. So we transform the 2D output, 2D images output in a 1D vector. And here we have a MLP. So we have a first layer here, 256 neurons. And at the end, we have the second perceptron layer, and with 10 outputs. So it means that we can classify 10 different clauses. Okay, so you will be able to test this one, as I explained that for the handwritten character. Okay, so we can use directly that in Google Colab. Just to finish my presentation, I will give you another example directly about another program that I have to show for you. Excuse me, is this one. Here it's an example of program how to, and it's using in fact all the programs that I have that you have now. Okay, so it's inside the examples that I have sent for you. Okay, through Professor Sarifudin. And so you have this example here. So and it's use also this databases. Okay, so this local databases. And for that, so as you can see, we can access to this databases. So for that, I use the SciP.io package. Okay, and I can, and its use, in fact, is very useful because, as you can see, .mat is in fact the MATLAB files representation. So you can exchange the files from MATLAB directly in Python using this package. So I can learn, I can load the MNIST databases, and here I can, in fact, access to this one. So, for example, here, so I have this one, so this variable here. So I have here this this size. So MNIST is the full databases, and here, as you can see, so I have the X, which is the full, in fact, databases because it's the size. In fact, 70K size, 70, okay, and this one, so I can access to one of these digits and to have the representation as I have shown here, okay? And just to finish also this one, here I have also written for you in fact, access this one used directly here is in fact this one, and this one is MLP, as you can see here. So for the example, it's the same that we have seen, in fact, with Google Colab, but directly using, in fact, this one with a spider. Okay, so you have the, in fact, the source file, which is here. So I use, in fact, the Keras dataset and so on. And here I want to recognize again the 10 different characters here. So I have 10 output at the end. And as you can see, again, so we have, in fact, it's the same program that we have seen with Google Colab. And I can just to run okay, as you can see here. So here I have 120, no, I have, excuse me, 20 epochs, as you can see. So it takes times to do the 20. So at the beginning, as you can see, okay, so now I have the second epoch and so on. And as you can see, the loss is 0.4 at the beginning, and after it will reduce and so on, okay? So maybe here, because I have 20 epochs, as you can see, it takes maybe a few minutes to do that, maybe 5 or 10 minutes, I don't know exactly, to do that. And that is what I wanted to show you. And you have this example in your package, okay? So thank you very much. Now I have finished my presentation during my lecture. Maybe if you want, we can take a few minutes to discuss together about maybe some questions that you want to ask. Okay, pour ça, I speak in French to Professor Sarifudin. Sari?
Oui, Michel.
Ouais. Donc, si on veut, s'ils veulent poser quelques questions, ou sinon, je pourrais répondre par mail comme ils veulent.
Je vais lui demander.
Ouais.
À l'instant, il y a la mosquée encore qui part, qui fait le azan. Juste une minute, s'il te plaît. Oke. Bagi yang ada yang mau tanya silahkan. Mau pakai bahasa Inggris silahkan, mau pakai bahasa Indonesia silahkan. Nanti saya terjemahkan. Silahkan. Kalau ada yang mau ditanyakan dari apa yang sudah disampaikan. Ada pertanyaan? Mumpung beliau buka sesi pertanyaan, sesi tanya jawab.
Ça, il n'y a pas de problème. Éventuellement, ce que tu peux, enfin, je vais leur redire, mais éventuellement, je peux échanger avec eux par mail s'ils veulent, enfin, des choses comme ça. Mais bon, voilà. Ok,
Ok.
je vais leur dire en anglais.
Ok.
Ok, vas-y.
Vas-y.
Ok, just understand for you, it begins to be late, okay, and maybe you are tired, and okay, because I gave for you a lot of informations. So I suggest for you to read again my slides and to maybe to test the example of programs that I gave for you. Okay, I suggest really to test that. And if you have some questions, don't hesitate to send me an email in English, and I will try to answer for you very quickly. Okay? So thanks a lot, and see you next time.
Ok. Michel, est-ce qu'on peut prendre, on peut prendre une photo?
Ah oui.
Tolong semuanya dihidupkan kameranya ya. Kita buat foto ya. Est-ce que tu peux comment dire, étendre ton PowerPoint, s'il te plaît?
Ouais, d'accord.
Pour que je puisse prendre toutes les personnes là.
Ouais, je vais le faire. Attends, juste une chose avant. Ce que je vais faire, je vais juste montrer une dernière chose. Okay, just to finish my discussion, as you have seen, now my program is finished. Okay, and at the end, so it was I run this program. So in this example, so the loss was this one, so the error was this one at the end after 28 epochs, and the accuracy, the performances, okay, is now the real accuracy is very good because it's more than 98%. Okay, so maybe if you can continue, maybe not 28, but maybe, I don't know, 48 or 50, okay, maybe the results should be better. You can test by yourself, okay? And to do that, you have just to change one parameter in the program. In fact, is this one. It's the size here of epochs. And okay, we have just to change that and to test again. Okay, just now I close. Okay. Voilà. C'est bon comme ça?
Oke, semuanya sudah buka video kameranya, silakan. Oke, ada yang mau ngambil foto? Ada yang bisa bantu ambil foto? Ya, 1, 2, 3. Bentar. Ya, dulu. Oke, halaman kedua. 1, 2, 3. Oke, makasih. Oke. Bon, merci beaucoup, Michel.
Merci beaucoup.
C'est très, très clair pour moi. J'espère que les étudiants auront plus de connaissances. Et je vais essayer de travailler avec eux.
D'accord. Tu veux qu'on continue de discuter un petit peu tous les deux ou pas, ou tu es fatigué?
Si tu as le temps.
J'ai un quart d'heure devant moi, donc on peut discuter. Ok, so see you. On discute tous les deux avec ce canal, je sais pas. Ouais. Ok. So see you next time. And ok. Ouais, donc.
Terima kasih semuanya. Silakan keluar ruangan.